All right, we'll just give it a minute here to let everybody filter in. All right. Hello, everybody, and welcome to today's webinar, Building Performance Simulation in Action, Case Studies from AIA COTE Winners, presented by the ibpsa-usa Education Committee. Today's session will be recorded and available through the ibpsa-usa YouTube channel. If you have any issues hearing the presentation, please try calling in by phone instead of using the computer audio. This is a Zoom webinar, so you can participate by posting questions and comments in the Q&A tab at the bottom of your screen. Questions will be viewable by all attendees, and there is an option to submit anonymously if you prefer. We will have a Q&A section towards the end of the webinar to address your questions, but feel free to input them as we go along. You can also upvote or comment on questions that resonate with you. This session is available or eligible for an AIA CEU. Please email admin@ibpsa.us, the email that you see at the bottom of the screen, to receive your credit. We welcome your questions, thoughts, and ideas as we continue to work towards ibpsa USA's mission of fostering better buildings through simulation. And I will now pass the time over to the chair of the Education Committee, Eric Kolderup.
Yeah, welcome everybody. So really excited about our three speakers today. Two very exciting projects that are award winners from the AIA's Committee on the Environment. So first speaker is David Mead. He heads the Regenerative Design Group at PAE, where he leads research, integrated engineering, whole life cycle carbon analysis and verification of concepts. He's committed advocate for regenerative buildings and brings an innovative approach to greenhouse gas and energy analysis to advance building performance towards a carbon neutral future. So thank you for joining us, David. Also with David is Rachel Rublik. She's a mechanical engineer at PAE with a passion also for regenerative design and healthy ecosystems and human interaction with the environment. So she's focused on integrated design, net zero energy, and living buildings, also passive design strategies, low carbon solutions, and healthy materials. So excited to have Rachel here. And then our third speaker who'll be talking about another project is Adam McKittrick. He is a mechanical engineer with CMTA, and he's got a background in energy modeling to assist in designing zero energy and high performance buildings. So really appreciate the three of you joining us. Now I will hand off to Rachel and David to talk about the PAE living building.
Great. Thanks, Eric. So today we'll be talking about the PAE Living Building, which is in Portland, Oregon. It did win AIA Community and Environment Award this year. And let's go skip over the next one fast, I guess, Rachel. Go to the next one. So just a little bit about PAE. If you're not familiar with us, we are mostly a West Coast firm. We started in Portland. We just opened a New York City office, which is pretty exciting. And we do work across the country. And we've been around for 57 years now. We're really known as leaders in sustainable design, especially for living building projects. We'll be touching on that here. Modeling for living buildings is very different than other building types. And we'll be touching on some highlights and lessons learned. Quick, if you're not familiar with AI Community and Environment, I used to lead, I was a co-chair for the Seattle group for years and was also involved with it in San Francisco. It's a great organization, a great partner group for ibpsa. There's a real mission that they have towards a healthy, sustainable, equitable future. And these awards have been around for a long time. If go to the next slide. It goes all the way back to 1997. And it's helped set a precedent for the architectural industry to set the highest caliber of sustainable design, and they're really coveted awards by firms. Firms are working to figure out, how do they deliver projects that can achieve this award level. And today we'll be focused on these two buildings, so the PA Living Building and then Thurston Hall renovation will be the next presentation. So Living Building Challenge, if you're not familiar with it, it's a third-party rating system. It was started by the International Living Future Institute. And the goal of it is to go beyond net zero into restorative systems. So if you look at traditional buildings like a code minimum building or even a green building that have a negative environmental impact, and even high performance and sustainable buildings still tend to have a lot of emissions, water resource challenges, material resource challenges. So the idea of the Living Building Challenge is to create restorative systems so that buildings generate more energy than they use. They help recharge aquifers and help create closed loops within the built environment. So there's 7 petals that you have to achieve, and this is a performance-based system. So you have to show that the building actually hits these performance targets. So from a modeling perspective, especially for water and energy, it takes much more detail to deliver buildings like this because you have to make sure the building's actually performing as predicted. So we worked on the Bullet Center as well. It's where I'm located right now. And it's another good example of, lessons learned. Even after the building's built, you have to keep monitoring it to make sure it's continues to hit the targets. The unofficial 8th petal, we kind of came up with this because the PA Living Building is the first developer-led living building, and it's to create a financially net positive project. Next slide. So it targeted a 10% internal rate of return over an anticipated 10-year hold with a 10% rent premium. And with that, and a number of other measures, with it being within an opportunity zone, kind of setting reasonable investor return rates, anchor tenant, which is PAE, so we take up a decent portion of the building, and low interest rates. Our team was able to work with our development partners to make this work financially. And that's a very unique solution and one of the most innovative parts of this project.
So the PA Living Building is a 5-story office building in historic downtown Portland with retail on level 1. It's designed to operate at an EUI of just under 20. It's been fully certified as a living building, and this means that it's operating at net positive energy and net zero water. So the energy petal requires that a building produces a minimum of 105% of its energy via renewable energy. With this goal of net positive energy and with the developer-driven building, we ended up running many model iterations to dial this building in and feel confident that it would meet its performance targets. So during early modeling, we did a number of facade studies. This is just a sampling. This iteration has a fairly efficient baseline. And you can see a lot of these envelope options did not have a dramatic impact. The biggest levers we found were window wall ratio, and then of course the solar heat gain coefficient. Driving that down not only reduces energy, but also has an impact on the mechanical system size, which then impacts cost. During this time, we also identified some of our challenges, lighting energy, and then plug loads. So I think this was a bit of a wake-up call for us as the anchor tenant, recognizing that as a data-heavy engineering firm, our IT loads and our workstation loads were quite high. So we considered 2 central plant options, a ground source and an air source. While a ground source plant is more efficient It is not dramatically so compared to an air source heat pump in Portland's relatively mild climate. It's also more expensive, so in the end, we decided to go with the air source option. These are the 6 main metrics by which we predict human occupant comfort. We considered all of these and plotted hourly data from the model or from various model runs into the psychrometric charts. We did that in an Excel-based add-on tool, and then use this to help determine how our design decisions were impacting comfort, particularly in some enclosed spaces like conference rooms. And then we dialed in our control strategies for how to keep on such an efficient building, which ended up relying mainly on radiant, how we could keep comfort high. We relied on natural ventilation as a passive cooling strategy and as a biophilic element to improve occupant satisfaction. We settled on a scheme that alternated manual and automatic operable windows. So you can see in this diagram at the bottom here, we had a casement style manual window that allows occupants to just crack a window open for a bit of fresh air, and then alternating with automatic windows that are a awning style, and these operate on a zonal level to really flush the building for passive cooling. And modeling this in IES, this uses a bulk airflow modeling to determine the impacts. So this is the HVAC system we landed on. You can see air source heat pumps on the roof, down to a refrigerant to water heat exchanger that then provides heating and chilled water to the radiant floors building. The radiant floor is the predominant means of heating and cooling. We also have energy recovery ventilators on each floor. And then we also have fan coils in select spaces, namely level 1, and then some densely occupied large conference rooms for additional heating and cooling. We wanted to maximize daylighting in the space, both for occupant comfort and then to reduce the lighting energy. We ran some daylighting analysis on this and looking at how far we could penetrate into the core and really allow people to choose not to turn lights on. One strategy we ended up using is upturning the beams at the north and south exterior grid line. This allowed the high beam to be eliminated and for the windows to be placed higher up on the wall. And that allows the daylight to penetrate deeper into the space. So in our previous office, we had conducted an occupant survey and found that employees that were piloting a hoteling program where they got to choose their seat each day, they reported a higher level of occupant comfort compared to those who had assigned seating. And so this highlights that people are diverse in their preference. Comfort is not a simple formula. Some people may want to sit by a window, where others may want to choose to be by a diffuser to get that cool air on them, while others get cold easily and don't want to be right next to a diffuser. And so for this building, we knew going into it that we were going to have 2 facades where we could maximize that daylighting quite a bit because they're bordered the street, and then 2 facades that border adjacent properties. And so the glazing there is more limited. And so we leaned into this and decided to go with 100% hoteling. So people come to the office each day and get to select or pre-select where they want to sit. They just reserve a desk. And this allows people to explore different seats. Some people may really want that nice daylight area. Some people actually prefer to work in a darker, cozier spot. All right, so this is how things landed in the final proposed building. You can see compared to the baseline. For this, we ended up modeling all the end uses at a much more detailed level. We modeled the water system since we had the water pedal, so that had a decent energy use associated with it. That was a lot of working with the designers there, estimating the loads, when those would operate. So a lot of spreadsheet calcs on that. We also dived into our plug loads, looking at our workstations. We metered our existing workstations. We metered our IT loads. We were metering our break rooms. We're looking at different, ice machines, and kind of just really digging in because we knew that we needed to be able to meet this 105% target of PV production. So we really wanted to get it as close as possible, without overspending on the PV side. And then, for example, you can also see we modeled the controls as well. And then this is just a high level look of it, how it compares to Architecture 2030. We're meeting or below the Architecture 2030 target. And then we ended up installing what we were estimating to be 110% of our energy needs for our own little safety factor there. So how does the project generate sufficient renewable energy? First, we maximize the PV on the roof area while still allowing for access around fire department and maintenance, and then also having limited mechanical equipment, locating that in that northwest corner and a little bit in the center there. But we still did not have enough to power a 5-story building. And since the building is in a historic district, we couldn't have PV overhang the building or be integrated into the walls. So we looked at other options. There is an exception in the Living Building Challenge for buildings in densely occupied zones, and that allow the PV to be installed off-site. The project had a general contractor on board very early, which I think was really important for the success of the project. And we worked with them to identify a nearby affordable housing project. And what we did is install the additional PV system on their roof, and basically those occupants get to keep the electrons in the sense that the system is net metered by the utility, and it reduces their energy bills, but the PA Living Building gets to keep the renewable energy credits. In the end, we think this is a win-win both for the community and to help the building meet its performance targets. So there was an additional challenge being located in the Portland downtown network. The local network has a limited ability for the PV system to feed into the grid. To handle this, we installed a microgrid, which is effectively a fancy controller that handles the generation sources and loads. We also installed a battery system that helps us harness the additional PV production. So by storing it into the battery when we can't feed more back to the grid, and then feeding that back at a later time. And it also gives some resilience so that we can island the building and keep things running even if the grid were to go out or there's some sort of local emergency kind of thing. All right, we also looked at our emissions, embodied, operational, and refrigerant emissions. This was kind of the early days of embodied emissions. Here we were using the Athena for studying the embodied emissions. We also worked closely with the contractor in terms of getting takeoffs of materials. And we studied a couple different structural systems. We ended up going with a hybrid mass timber system with a concrete core, and compared to a COTE steel building, we were able to save almost 50% embodied emissions. Once we took into account the biogenic nature of the wood, this was FSC, sustainably harvested wood. We also were able to reduce the operational emissions by over 50% just with all the energy savings. And then we also strove to reduce refrigerant emissions by strategically locating that refrigerant piping. We had like a single chase going down rather than basically minimizing the amount of refrigerant piping that was in the building, converting from refrigerant to water. That sort of thing. Oh, and also using brazed fittings, which are shown to leak less. And in the end, we offset the upfront embodied emissions as well to get achieve a carbon negative. We also looked at the PV array. This does have a significant embodied emissions associated with it. And then we compared that to the operational emission savings that we get as it generates electricity. And we found that while it's significant that upfront, we see a payback sometime during year 3 or by year 3. And then it's carbon negative after that. There's still more work to be done on the PV side of things, especially on the recycling of this and having a more robust system in place. All right, so that brings me to net positive water. For the Living Building Challenge, 100% of the water used on site must be captured from rainfall that falls onto the building footprint. So what we did is we collect water from the roof, and it gets stored into a 55,000 gallon underground cistern. This is then treated to potable standards and piped through the building, as you can see in the schematic here. This is a picture of in the mechanical room. The cistern is below this with the hatch. You can see at the bottom there. You can see the treatment skid. It's a number of filtration systems and then our filters, and then a UV system that then pipes into a day tank for distribution through the building. All right, so this is that same schematic with the gray water system added in. So what happens is we collect water from the lavatories and the showers that goes into the storage and treatment system for gray water, and then that's pumped out to the urinals and vacuum water closets. And those vacuum water closets are very, very small amount of water use, and then the urinals flush, are urineless, except they flush every 72 hours and clean things out. And so basically we're recycling, reusing that water. So, but we still wanted to do more. Typically we have this broken system for the nutrient cycle. Nutrients come in and they flow out and go to versus cycling back kind of as nature would intend. So we tried to close this loop by installing a nutrient recovery system. So you can see here that we're collecting urine from the urinals. This goes into an underground storage tank, and when this gets full, it's batch processed into a treatment system. It's a distillation process that then converts it into fertilizer that is now sold at local nurseries. And this is one of those energy loads I talked about that we looked at estimating to make sure we were producing enough renewable energy to cover it. So this is in summary looking at comparing a code building to kind of that typical low flow building. Yes, we can get a 20% savings, but with the PA living building, we reduce that much more so with those composting toilets and gray water reuse. And then because we are not using any municipal waters, all rainwater, we get down to that 0.
So that wraps up this quick presentation, and just want to thank everybody for joining, and also wanted to let you know we are looking for talented modelers and engineers. So if you're interested, we'd love to have you join us. That's it.
Thank you.
Thank you, Rachel and David. So yeah, now I know there's a few questions that come in. I hope you guys don't mind that we hold those until after Adam's presentation. But Adam, please go ahead.
Sorry, is it showing up for everyone?
It's good, thank you.
Okay, great. Good morning, everyone. I appreciate the opportunity to speak with you all today about this project. My name is Adam McKittrick. I'm a mechanical engineer working for CMTA. We're a MEP design firm, and we're based out of Louisville, Kentucky. So what I'll be covering today is essentially a case study on the renovation of Thurston Hall. And this was a historic dormitory that was part of the George Washington University campus in Washington, D.C. So just a high-level overview of this project. This is a historic building. It was constructed about 100 years ago. It was originally an apartment building, but was purchased and converted into a dormitory in the early 1960s. It's a roughly 200,000 square foot building. We have 9 floors that are residence floors, and those are housing about 800 freshmen every year. And we've also have a basement level, which is a dining facility for students that are living in this dorm. And it was actually expanded and overhauled as part of this renovation to hopefully the goal was to serve instead of just serving breakfast, serve additional meals for every day. And because of where Thurston Hall is located on the GW campus, this dining facility was seeing a lot of traffic from the nearby dorms that were kind of outside of the central heart of campus. So this food service component was a big increase in energy consumption compared to the pre-renovation building. And I want to bring that up just because it's gonna have driven a lot of the design decisions around some of the energy compliance that needed to be met for this project. So this kind of leads me to the first overarching design goal, which is to meet current and future building energy performance standard requirements is BEPS. This is a DC specific energy efficiency target, and it applies to all buildings in DC at this point, whether they're existing or new construction, even if they weren't being renovated or changed. This is a mandatory energy efficiency improvement for all buildings. So the goal that we have here was to provide a design which meets these BEPS compliance targets for both cycles. So there's 2 cycles that are currently planned. We're in the middle of the first one now, which is going to end in 2026, and there's an additional second cycle ending in 2032. During each of these compliance cycles, we're looking at a certain source energy reduction, a source EUI reduction that must be achieved. At the time of this design, which was starting in 2019, we did know what the first target would be, which is a 20% energy improvement. But the target for the second cycle is still up in the air. So it hasn't been disclosed. It wasn't at the time of the design, and it still is not known and will not be until 2027 when the district reviews the first cycle in compliance for all these buildings. This is a big challenge for us because we're trying to meet this unknown target, and there's also a fairly large compliance penalty that would be applied if you don't meet these targets. In the case of this building, it would be as much as $2 million for each of these cycles. So of course that's a huge number, and the university really wanted us to give them a strong idea of how we would expect the building to operate from an energy standpoint and how that would fall into these 2 BEPS compliance cycles. So in order to answer that question for the university, we first started with determining what the BEPS benchmark would be and the subsequent targets that would need to be achieved under the 2 compliance cycles. So this is all calculated using source EUI. And what we're looking at is during this first cycle needing to achieve a 193 EUI for source energy. And then, under BEPS 2, like I said, we don't know what that was going to look like in terms of a target, but we're assuming another 20% improvement to be on the safe side. So that would bring us down to a source EUI of about 155. So, at this point in the design, we created a high-level energy model. This is right at the beginning of the DD phase for this project. And based off of our initial discussions with GEW, certain design choices, primarily the fact that they wanted us to design around a 4-pipe fan coil system, as other dorms on the campus also use fan coils that were in the renovation process as well. So they wanted to have consistency with those. So at that point, we took all of this initial design data, and our energy model was coming out to a site EUI of about just a little over 80 and a source EUI of around 200. So the reason I was mentioning the food service component in particular is that this BEPS benchmark doesn't distinguish between a typical dormitory, typical residence hall, versus one like Thurston, which with this food service component, we're going to have much higher energy consumption in the building, because we're serving 3 meals a day and running an entire kitchen for 13 to 14 hours every single day. So this makes achieving that BEPS target much more difficult, because without that kitchen energy consumption, we're looking at a source EUI of around 153. So we'd already be meeting both of these compliance targets without much of any difficulty at all. And that's with what is honestly kind of a middle of the road HVAC design from an efficiency standpoint. So at this point, we presented this information to the university and let them know that we would need to continue to evaluate other ways to save energy while still giving them the mechanical system that they desired. But during these conversations, like, I want to take a step back because this is more of a general point, but something that CMTA puts a lot of emphasis on is collecting real world performance data. So what I'm showing here on the screen is a internal tracking tool. And this lets us document, project data, who was involved in the design, what type of HVAC systems we're looking at, energy and water performance, construction costs, all kinds of different metrics. And right now we have about 450 projects that we're actively or have completed tracking. So we try to do this on every major project that we have, and having access to this kind of data is very powerful in combination with some of this high level energy modeling at the beginning of a project. So for example, on Thurston, we had 6 other residence halls that were of similar scope, minus the food service component, that were also located in the same climate zone. So that gave us additional data points to help validate some of the early energy modeling results. And particularly early in these phases of design, we have found that energy modeling can really suffer from putting bad data into it and getting bad data out. So being able to leverage historical performance data for our own projects is very valuable to us, and it helped a lot with these conversations with GW initially. So with our overarching goal, which is to improve energy performance in the building, and to meet these BEPS requirements, we were looking at the envelope in particular. This is a 100-year-old envelope, and it had seen very little improvements over the life of the building. One really critical area that we needed to address was water infiltration through the window framing. You can see this IR photo, which is showing just where we have water leakage, and this is very common throughout the entire building. And another issue too that we were seeing was, of course, this was this is an old envelope, so our exterior walls were brick and interior gypsum. We had no insulation or anything like that. So this is we had it tested, and it was performing at about an R2, our value of 2. So that's not going to help us too much on the energy side. So we ended up having a conversation with the architect here about needing to fur out the walls in order to add insulation and new gypsum board on the interior, as well as to repair the envelope where we have problems with water and air leakage. It wasn't really ideal necessarily to reduce the size of these dorm spaces. They're already on the smaller side as it is, but it was a critical step that we needed to take to reduce energy consumption, as well as just to provide a more comfortable living space for the students. So what we ended up doing was using Therm to model various insulation options, so wall assembly options, looking at just like vertical insulation as well as insulation surrounding the beams that are separating each of our floors. The goal here was to be able to analyze the effectiveness of various insulation strategies. And the end goal, we got a realistic wall R value that we could use in the energy model. I guess the last kind of big ticket item that we were focusing on was the need to improve air quality in the building. We were tracking this pre-renovation during a summer occupancy period, and the graph you're looking at here is showing a typical day where we had occupied CO2 levels that were significantly higher than we wanted them to be. These were both tracked in a two-person bedroom. We had some that had one occupant, some that had two occupants during this this summer period. And we measured a full week's worth of data, and this is the average of what we found. So we're seeing CO2 levels that are double and triple what we'd like to see in a typical design. So at this point, this is with the existing mechanical systems. Outside air is being brought in through unit ventilators. So our strategy here, we know we need to increase our ventilation rates, but we have an energy limitation where we're trying to save energy, reduce energy, and bringing in more outside air is going to increase that using those unit ventilators. So we decided to provide a dedicated outside air system, which would give us two benefits. First, we can improve our air quality. We used MERV 8 pre-filters and HEPA final filters at each DOAS. So that was bringing in the cleanest air that we possibly could. And since we were increasing ventilation rates, we couldn't afford a huge energy penalty there. So using a dedicated outside air system with energy recovery between your intake and exhaust air, allowed us to meet that goal of increasing ventilation. And actually, our modeling was showing that we were going to be using slightly less energy overall. So, at this point in the design of the building, we know we're not meeting the BEPS requirements, but we're still trying to follow the university's preference towards, the system that they like to have in this building, just because their maintenance staff in particular was comfortable working with this type of system. So we were planning to use, their existing, natural gas condensing boilers. Those have just been replaced a few years before this renovation started. And those were actually in quite good shape. There was a chiller that was serving this building as well as a nearby building as well, Mitchell Hall. So that was going to need to be replaced along with the cooling tower that serves that. And we're looking at the 4-pipe fan coils in the dedicated outside air system for our ventilation. So this is kind of our starting point when looking at our energy performance. But we needed to continue pushing a bit further to comply with BEPS. So the next step for us was to continue revising the energy model so that it was detailed and robust enough to evaluate certain energy saving measures that were separate from our HVAC system. So we really looked at, we have a bunch of items that we were evaluating, kind of grouped those into priority items, and then some stretch ones that were less likely due to budget constraints, and as well as smaller energy and cost savings that we were anticipating on those. So the table at the bottom here is showing which ECMs that we deem to be effective and that were ending up being incorporated into the design. Particularly, the envelope, we were seeing roughly 10 UI just there, as well as some savings due to to control ventilation and using less water in showers and stuff like that. So at the end of this, we're looking at a combined site UI of about 70 and a source UI of 170. So I just want to point out that's not actually meeting the BEPS cycle 2 requirements that we're anticipating, which would be a source UI of 155. So at this point, we're calculating out what that penalty would be, and it's going to be roughly $1 million in 2032 if this was how the design would progress. So at this point, it's time to bring this information to GW, and our goal was here to push for a more efficient HVAC system choice. They have their strong preferences, but we're trying to show using our energy modeling results that making the case for a different HVAC system. And our goal here was a water source heat pump system, which would be significantly more efficient than the fan coils. And we had a few selling points here just beyond the financial penalty through BEPS. And it actually turns out this would have a lower first cost just because we're switching to a 2-pipe hydronic system versus the 4-pipe fan coils. So we're eliminating half the piping in the building, as well as we're not needing to replace the existing chiller, just the cooling tower only. So while the individual heat pump units themselves were slightly more expensive than the fan coils, the net cost overall ended up being roughly $500,000 cheaper. And the second benefit that we brought to them was we have added resiliency with having distributed compressors throughout your building. So if one compressor fails, only that individual dorm room would be affected, versus if your compressor on your chiller fails, we have no redundancy on the chiller. You're going to lose cooling for the entire building. So at that point, the main hurdle for GW was maintenance concerns, like I've mentioned, because the downside of having distributed compressors would be if one of those fails, they're not easily accessible to maintenance staff without disrupting students in their dorm spaces. So that is something that we discussed with them. But at the end of the day, the energy modeling that we were showing them, it was showing that the ECMs alone weren't going to bring Thurston Hall into BEPS compliance. So that's ultimately what convinced GW and their maintenance staff that going towards the water source heat pump system was the best path going forward. So ultimately, we ended up revising the HVAC design as well as the energy model to reflect this new system type. And that brought our site EUI down to a little over 63, and that's including the kitchen as well. So this graph here is just showing that we're really close to compliance in that second BEPS cycle, within an EUI or so on the source side of things. So our fine, instead of being about $1 million, was going to be about 30,000. So that's a little more tolerable to GW. In reality, with the addition of a small amount of renewable energy that we had on the roof from a PV system, that offset about 4% of the building's energy consumption, in addition to the numbers that you see here. So the fine, there would be no fine under BEPS 2 when that's taken into account. So it's one thing to be able to promise GW that this design is going to meet these targets, and energy modeling can be very powerful in that way. But we've been operating this building for a couple of years, so the real question is, did it actually perform that way? And we've seen some that do, some that don't. And in this case, after the first full year of operation, students moved in fall of 2022. We ended up with an EUI of 63.6. So that's basically spot on to the energy model. And typically I'm pretty happy if we're plus or minus 5%. I know there's a lot of things that maybe don't get picked up in an energy model in terms of how the building will be operated and controls. But it's rewarding to see someone ended up so close to the actual consumption. I think the biggest takeaway for me here was really working closely with GW to figure out scheduling for the building, everything from breaks, when students can and can't use the building, how is it going to be operated for summer students, what would our food service hours look like, does that vary on weekdays, weekends, those kind of details. Those are all really critical into putting good data into this energy model, which let us get good data back out of it. I've talked about this kind of from the standpoint of a mechanical engineer and how CMTA went through the MEP design process, but I just want to highlight a few other features of the building through the COTE framework, because this project did win the 2024 COTE award, or one of the awards. So some of the ones that really stuck out to me were, you know, on the ecology side, the green roof, as well as the vegetation throughout the courtyard. I think it's really important. This is someone's, you know, this is someone's home, but it's in a very dense urban area. So having some connection to nature, even if it's small, is really helpful here. Also, you know, there's a really cool rainwater collection system. There's a cistern, and all the drainage from the courtyard and from roof drains is stored and reused for irrigation, and it covers the entire irrigation needs of the building. So that's quite a neat feature there. And, you know, tying back into some of the air quality concerns as well, we ended up measuring our post-occupancy CO2 performance, and between all of the dorms that we measured, we were below 800 parts per million on average. So that's, you know, that's fantastic considering what those numbers were like before. And, you know, it's important that this really just helps contribute to a healthier living environment for the students that spend their year here. So I thought this was a really great project that pulled in a lot of fantastic ideas and made them a reality. And I just wanted to, you know, finish up by giving a shout out to VMDO, and in particular, Michelle Amt. And, you know, she was really the leading force on a lot of these items on the architectural side, and this wouldn't have happened without her involvement here. So I'll go ahead and turn it back over. I believe there's some questions that have showed up, and then both teams can answer those. Thank you.
Yeah. Yeah. So thank you very much, Adam and Rachel and David. So I want to invite Rachel and David back into the scene. And yeah, we do have a few questions. And for those of you who haven't asked your question yet, please use the Q&A feature down at the bottom. Maybe we'll start with a question from Matt, and I think this is for Rachel and David about the operational carbon emissions. So how did you calculate your operational carbon emissions? Did you use hourly grid factors or historic or projected grid emissions?
Sure. Yeah. So we use the local utility emission factors. We had developed an internal tool to look at this, convert energy into emissions by utility. This has developed, this was a few years ago now, where we now look deeper at the hourly emissions, looking at cambium and other data. But there's, you can have a whole, I think, a whole presentation on hourly data and kind of the intricacies and weather, and also projected data. Had a project that where we looked at the utility's projection. They were trying to get to net zero emissions by 2040, and you know, just over the course of a couple of years, they weren't meeting their projections. You know, but are still trying. So yeah, it's a complicated conversation there.
Yeah, thanks, Rachel. This is obviously an evolving subject for all of us analysts. So second question, another question for Matt about the difference between the predicted EUI and the actual EUI for your living building challenge. And
yeah, so we had predicted a 19.5 EUI. We were certified this past year, coming in at a 16.2. So better than we had expected. There's a number of factors there. You know, we post-pandemic, I feel like we don't have as many people as we had expected. And we are, in terms of individual, I think you had asked some different in the end uses. Yeah, so our IT loads were actually less than we had expected. We worked really hard on those, working with our IT department, trying to reduce just the number of switches that were going, since they're kind of just running all the time. We ended up going with an all Wi-Fi model instead of hardwired and Wi-Fi, so that helped. Our lighting is a challenge still. We've got really efficient lighting in there, but the controls there, really dialing in the controls and not having issues with that control system has been a bit of a challenge.
thanks. Yeah, I think all of us face uncertainties and these predictions that we're sort of learning how to deal with. So Matt's kind of monopolizing the first couple questions here. But this is kind of a general question, and maybe both of you can, take a stab at this. Like, how many important decisions were guided by modeling? Like, without modeling and just using heuristics or best practice? And, how much worse would the building perform in terms of operational or embodied carbon? So like, what's the marginal impact of using modeling versus just rules of thumb?
Any living building project, we always use models. It is a fool's errand to go with heuristics in my experience. So yeah, you have to really dial it in. Otherwise, you will not get close.
Yeah, I guess Adam, do you have? Oh, sorry, Rachel.
Well, I was just going to add on to that, I think, experience helped us kind of start in a good spot. And we had experience from past projects. And so then it's really the fine tuning, and it also allowed us to dive into the plug loads and really fine tune that. So I think you can use your experience, but yeah, I agree with David that really wanted to go with modeling to dial it in.
Yeah, I'll echo something kind of similar to what Rachel just said, where, we have experience, we have a lot of data that we've tracked for similar projects, but it's also a really great tool just to convey that, we can say that we think it'll perform a certain way, but, being able to put some numbers behind that and be able to show, graphics from energy software, like that's been a great tool for us as well, just to, convey to an owner, this is what we expect.
I'm going to jump in on one more item. One thing that we used for this is we had the microgrid. And so we used the energy model results to figure out kind of what our base load was and kind of what our peaks were going to be in terms of figuring out sizing of the battery and that feedback to the grid and modeling that on an hourly basis. What will be interesting as we kind of move into more grid interactive buildings, how accurate some of the modeling is versus actual. So that I don't have a great handle on. I think it'd be good go back and study that.
Right. So not only are we going to have to like dial in our assumptions to kind of get our annual energy right, we're going to have to get our minute by minute energy modeling results right. So what you're saying?
Yeah,
Right.
like load modeling is really different than energy modeling, and we're kind of, forefront of that right now. So yeah. And we're using IES. I saw someone asking. So ISVE.
Yeah, I think and Adam, just on that question about the tools that you find useful.
Yeah, so this started really heavily on the energy side early in 2019. At that point, I was using eQuest, but throughout the design process, it took a year and a half or so. I switched over to IES in the middle of that, but I did use eQuest for some of the energy compliance at the end. But I had two energy models going at the same time, which is getting into IES at the moment. So it was kind of like a validation that we felt confident with the numbers there.
All right. So there's I guess some kind of questions about the project designs. So the PA building, there was the natural ventilation scheme that you guys talked about. So there's a question about how do you handle the building pressurization and then occupant discipline, like, leaving the windows open or doing incorrect control of windows.
Yeah, it's a good question. So I think our occupants are really engaged. So that's great. It's a great building to be in, to work in. But with the manual windows, that is a risk of leaving them open. The automatic windows, obviously, the building control system handles that. In past projects, I've done where I put window contactors in the manual windows so that facilities can see if any are left open. So this would be more like in a school building, and so they can walk around and target, oh, it's this classroom, I need to go close that window. We did not do that here since smaller building and just, you know, the economics of it all. So we kind of just walk around and make sure things are shut if for some reason someone's left it open. And then on the pressurization piece, we are not controlling the building pressurization. There's no medium pressure system here. But it did take a couple goes on the tab, the balancing to make sure things were dialed in on the supply and exhaust, and we weren't having issues, particularly, you know, with the composting system and everything. We really wanted to make sure we had that right.
Great. Another question on the modeling tools, I guess, from the perspective of the baselines and how you created the baseline models. Did these tools that you used generate them automatically, or were you, creating manual baselines?
For the living building challenge, the baseline's net positive energy, so it's a little different. There, like, you don't really have a baseline like what Adam was talking about.
Right.
Yeah, in terms of the baseline on Thurston Hall, it was essentially, it's manually created, but using IES, it helps you, get some things pulled in, depending on what your baseline is following. It was ASHRAE or ICC, but it ends up being a manual process for the most part.
Okay. And I guess maybe a follow-up for Adam on, since you were modeling an existing building, were there specific steps you take to validate your model or improve your input accuracy that you
something that we
share?
do that helps us, especially on the understanding, where we typically would see energy going in buildings. We on all of these buildings that we track energy on, we try, not all of them have the budget for it, but we try to sub-meter the end uses for, HVAC systems, for lighting, plug loads, kitchen equipment, all of that. So that gave us a really good foundational understanding of, for what we would expect for this building. And that along with some detailed conversations with the owner, I think is what helped get us fairly close on the energy model.
Okay. And one follow-up question from Michael about wall assembly testing to determine their R values. Did you do in situ testing?
Yes, we did. Yeah, it was a third party that came in to test that. They had a probe that they put through the wall, and they were able to run a current through it, or measure the heat flux somehow. I couldn't speak to exactly how that works, but it's a somewhat intrusive process that maybe is not always necessary, but we did have that done here.
And maybe time for one more question, which is not an easy one, I think. And this is directly to you, Adam, about the building performance standard policy and how you frame your contracts in case your energy modeling is wrong, the building doesn't get target. But I think for any project, like a living building project, if you've promised a living building, you've got a hard target. Anything to share there from a contractual side on how to approach this?
Wish I could speak to that more. Our project manager on this project in particular took care of all of that. And since it looks like we're going to be meeting that, I haven't heard anything about, what would be the process if we didn't. But no, that would be definitely something that I should probably know for the future if we ever have to deal with that.
We've had contracts we've had to negotiate like that before, where there's penalties if it doesn't hit it. There has to be really close coordination with the owner, because obviously as a design team and modeling team, we don't have control how it's being operated. So it needs to be a fair agreement, so it's not like a big stick for people who don't have control over it. But yeah, it's always negotiated, and there's more coming like that. So it's a great question.
Right. Well, I think that's probably all the time we have for questions. I did want to try to ask you guys about the level of effort that you face in terms of analysis on these projects where you've got these absolute targets that you're trying to meet. I think the answer is probably it's a big level of effort, if that's fair. But something to keep in mind for everybody in the audience, that these are challenges that are not trivial challenges. And thank you very much, David and Rachel and Adam. It was really great to hear about these amazing projects. I'll hand it over to Jackie just to close us out today.
Yeah, thank you. And thank you, Eric, so much for helping moderate the Q&A and the session itself. Please check out the ibpsa-usa website at ibpsa.us for upcoming events and other webinars and chapter events. For those of you watching on YouTube, please like the video and subscribe to our YouTube channel. And on the screen, again, the email is admin@ibpsa.us to get your AIA credit. Thank you, everybody, for joining us today, and have a wonderful day and a good weekend.